So you see, using the ALDEF, Langley's test truck, and the Convair 990 to test tires and tire wear really helped engineers solve their problem with the shuttle runway at Kennedy Space Center.
Right. They run tests, measure and collect data, graph the results,
and predict solutions to their problems. Sounds similar to what you do in your classroom?
Does NASA Langley conduct any other extreme tests?
Funny you should ask. Remember the title of today's program? Measurement, ratios, and graphing? 3, 2, 1, crash? Well, NASA Langley actually crashes aircraft to test them for safety, right here at the Impact Dynamics Research Facility.
How is technology used to collect the mathematical data in crash tests?
Why is area important in the results of the test?
How are ratios used to find a solution?
The Impact Dynamics Research Facility is used to conduct full-scale crash tests of aircraft. The aircraft to be tested is suspended from the gantry, pulled back to a calculated release height, and then released to swing like a pendulum into the impact surface below. Just before crashing, the swing cables are released and the aircraft goes into free flight. The cables attached to the aircraft are released by pyrotechnics or explosions. It's pretty cool to watch. We crash aircraft so we can see how safe they are and develop ways to make them safer. IDRF is very similar to what the auto industry does with cars. Everyone has seen the commercials with cars being crashed into barriers and the crash dummies responding to the forces. Our crash test dummies are wired with sensors and data are collected to determine the crashworthiness of an aircraft. Crashworthiness is how well an aircraft protects passengers in the event of a crash. We use the data from the dummies to make improvements to aircraft designs for crashworthiness.
Lisa, that is just so cool. I mean, you get to crash things for a living.
and we get safer aircraft.
You're right, Dan. The testing and the research conducted at the IDRF can really benefit all airplane passengers. One of our main goals is to reduce the force on airplane passengers during a crash. We want to create structures and materials that dissipate or absorb the energy from a crash before the energy gets to the passengers. Take a car, for instance. Structures like the bumper and frame are designed to crush. When these parts crush, they dissipate or absorb some of the energy so that the passengers are less likely to be injured.
Lisa, we all know that planes don't have bumpers.
Right. However, there are parts of an aircraft that can absorb energy in a crash. Parts like the subfloor, which is the area under the floor, the landing gear, the seat, and even the cushion can absorb energy. Restraints, like the seat belts, are also necessary to keep the passengers from flying through the aircraft during the crash. When these parts and structures are designed correctly or optimized, the passengers have a better chance of surviving a crash.
But Lisa, how do you design aircraft parts to absorb energy?
Good question. We use human tolerance data and crash test dummy data to develop better energy absorbing designs. You see, aircraft are made of different materials. Some are made of metals like aluminum, and some are made of composite materials like graphite or fiberglass. A tennis racket is a good example of a graphite material, and most small boats are made of fiberglass. Metals and composites perform very differently in a crash, so we have to design the parts to complement the materials the aircraft is made of. Basically, we would not design a subfloor in a composite aircraft the same way we would design a subfloor in a metal aircraft.
Can you really design a subfloor that absorbs energy?
Yes, in 1994 we tested a graphite aircraft called the Lear fan. When the original aircraft was released from the gantry, it was extremely rigid and nothing crushed. According to the crash test dummy data we collected, only one of the 6 passengers survived. So we used that data to design a new energy-absorbing or crushable subfloor. It would be like putting a bumper under the floor. Then we built and tested small sections of different subfloor designs until we had the best design. A second Lear fan was modified by installing the newly designed subfloor and tested. The results showed that the new subfloor improved the Lear fan's crashworthiness by reducing the forces on the passengers.
Oh wow, this looks crazy. How do you collect the data from the crash tests?
We use a digital data collection system that's designed to handle the impacts of a crash, not like this one. All the instruments on board are wired to the data collection system, and after the test, the data are downloaded onto a laptop computer to be analyzed by the researchers.
In school, we analyze data and we make graphs. Is that what you do?
Absolutely. We make graphs of the data collected and compare those to other graphs. This graph from an actual test conducted here at IDRF shows the ratio of G-force to time. You can feel the sensation of G-forces when you ride on a roller coaster. It's what you feel pushing you into your seat on a loop. As you can see, our graph has a curve shape. Next, we calculated the area under the curve and compared it to a human tolerance graph. This graph shows the maximum energy or G-force a human can tolerate over a specific time. The plot goes from 0G to 50G and back to 0G in a very short amount of time. The shaded area within the triangle is the amount of energy a human can tolerate in 100 milliseconds. Next, we set up a ratio. By comparing the shaded area under the dummy data to the shaded area under the human tolerance data, we can determine if the passengers survived. We want this ratio to be less than or equal to 1 if passengers are to survive.
Okay, Lisa, I have one more question for you. How does all the information that you collect here help aircraft safety?
By using measurements and graphs, we present the data collected from tests at the IDRF to the aircraft companies and to the FAA or the Federal Aviation Administration. Then the aircraft companies can use the new designs of their aircraft. The FAA may use the information to establish new rules and regulations for aircraft safety.